Welcome to our e-learning module on temperature sensor theory. In this module, we will explore the theory behind the design and use of temperature sensors. Temperature measurement is very important in most processes and can be critical to the life of a machine and its components. The three main purposes to use a temperature sensor are monitoring, regulating, safety. Temperature measurement can be used by a controller to adjust various processes, such as cooling an engine, optimizing combustion, heating fuel oil, preventing bearing failure, and many other processes. Temperature is one of the most commonly monitored parameters and can indicate inefficiency in a system and wear of components. Danfoss industrial automation temperature sensors use three different element types, which are produced by various suppliers. The first element type is the RTD, which produces a highly accurate standardized output curve that is ideal for many installations. The second element type is the thermistor, which comes in either a NTC or PTC variation and is the optimum choice for OEMs. The last but not least sensor element type is the thermocouple. The thermocouple is a well-established technology with high temperature capabilities which exceed the other element types. We will start looking at the RTD element type. The image on this page shows the construction of the RTD thin film element. A platinum layer of 1 micrometer is sprayed onto a ceramic plate. The layer is shaped by means of laser or a lithographic process. The element is then calibrated. To obtain the best accuracy, a laser is used in the calibration process. The element is covered with a 10 to 15 micrometer thick glass layer. The connection wires are mounted and fixed with a drop of glass. This RTD thin film element is the most common RTD element type used by Danfoss industrial automation. The RTD element has various qualities associated with it to differentiate this element type from the others used by Danfoss industrial automation. The RTD element has a nearly linear output curve over a wide temperature range. RTDs are defined by an international standard which regulates their output curve. They are good for use in heavy-duty applications. RTDs can have a high resistance level at certain temperatures, which produces a stronger signal than other technologies such as thermocouples. The international regulation of RTDs in common use makes it easy to find spare parts. RTDs have two main weaknesses compared to other element types. RTDs typically have a higher cost than thermistors, and the resolution is also lower at certain temperatures. This is due to a less steep output curve. The acronym NTC stands for Negative Temperature Characteristic, which describes the relationship between output resistance and temperature increase for this type of thermistor. The output signal in ohms decreases when the applied temperature increases for the NTC element. The temperature range is normally up to 150 degrees Celsius, with special versions up to 300 degrees Celsius. There are many different output characteristics which are not standardized by an industry norm. An NTC is normally defined by its output value at 25 degrees Celsius. For example, an NTC 10,000 will have 10,000 ohms resistance at 25 degrees Celsius. The tolerances are normally wider than for RTD, but you can get special accurate versions at a higher cost. The NTC is more commonly used than the PTC. The acronym PTC stands for Positive Temperature Characteristic, which commonly describes the relationship between output resistance and temperature increase for this thermistor. The output signal in ohms increases when the applied temperature increases for the PTC element. PTCs are only available in versions up to 150 degrees Celsius and feature fewer characteristic options compared to the NTC element. None of them are standardized to an industry norm. Like NTCs, the PTC's nominal value are described at 25 degrees Celsius. The tolerances for PTC are normally wider than for RTDs. The strengths of the PTCs and NTCs are: NTC elements have high resistance values, which allow for installation without the use of compensation cables, as the lead resistance in the wires will have very little effect. The negative temperature characteristic can be as large as several percent per degree Celsius, which allows the NTC element to detect minute changes in temperature. The NTC is also a lower cost element compared to RTD, which makes it attractive for OEM applications. Its lack of standardized output curves requires more intensive design integration and not plug-and-play as RTD elements. The lack of spare part availability protects OEM aftermarket business. Steep resistance curves allow OEMs to have a very high resolution on small application-specific temperature ranges. Thermistors can be very small, which makes them susceptible to self-heating errors. The weaknesses for the PTCs and NTCs are the mechanically weak construction, not standardized. Thermocouples are the oldest technology, as the thermocouple principle was discovered in 1822 by Thomas Johann Seebeck. It was first used for temperature measurement in 1862. A thermocouple consists of two dissimilar metals joined together at one end, which produces a small, unique voltage at a given temperature. The two metals can be welded, soldered, or otherwise joined together. The thermocouple is a very robust temperature sensor element and can be used at very high temperatures. Thermocouples have been used for many years in various applications. It is a relatively low-cost temperature sensor element and is regulated by an international standard. Generally, thermocouples are very reliable, but there are a few weak points. The thermoelectric voltage created is a small microvolt per degree signal. The measurement is a non-linear relative measurement, and special compensation cables have to be used to ensure a proper temperature reading. When working with thermocouples, moisture is enemy number one. It is very important to protect the sensor against moisture penetrating into the filling material during production and in the application. If moisture penetrates into the filling material, a short circuit can develop between the thermocouple wires, and this short circuit will act as a new thermocouple, corrupting the measurement. As mentioned previously, thermocouples require the use of special installation cables. Normally, the signal from the thermocouple is located at some distance from the point of measurement. Using normal copper wires will give problems because you create a new thermocouple junction at the connection of the copper wire and thermocouple wire. To avoid the problems, you must use compensating cables. The cables have to be made of the same material as the thermocouple or materials which have the same characteristics. Extension cables are manufactured with wires of the same composition as the wires of the corresponding thermocouples. They are coded with the letter X, placed after the thermocouple code. Compensation cables are manufactured with wires of different stranding or material to the wires of the corresponding thermocouples. They are marked by the letter C, placed after the thermocouple code. Different alloys can be used for the same type of thermocouple. They can be distinguished by extra letters, for example, KCA and KCB. When used within the temperature rating of the cable, the two options are equally good. But if you use the compensating cables outside the specified temperature range, you will get an error on the temperature measurement. The cost of the various cables is most often the decision criteria when choosing between the two. In the table, you can compare the characteristics of the different sensor elements. It is not possible from the table to generally conclude which element is the best one. It all depends on the application and customer preferences. Thanks for listening.